Hello and welcome back to the Pony80 channel. Thanks for joining me. Today we're going to discuss the memory we're going to be using on the Pony80. I have several requirements for the memory. One, I want 8K of ROM. This will hold the BIOS initially, but eventually can include CPM or BASIC. And since the Z80 address bus has 16 bits, it can address 64K of memory, so I want 64K of RAM. Now, I may want to utilize all 64K of RAM, so I want to be able to page ROM out, giving access to RAM in place of the ROM. I also want to be able to page the ROM in and out using an I/O port on the Z80. That way I can page it in or out via software. So let's map out what this memory will look like when we assemble it. On power up, the Z80 starts executing instructions at memory location 0, so it will need to have ROM at that location to give the computer the instructions needed to boot. So from 0 to 8191, or 1FFF in hex, we'll have the ROM. This will hold the boot up sequence and a simple operating system. And then after that, we'll have 56K of RAM. Basically from 8192 or 2000 in hex to FFFF. Now, we'll also need 8K of RAM to replace the ROM that we'll be paging out. So from 0 to 1FFF, we'll need some RAM as well. So if we go back to our list that we have up here, we've created the memory map of our 8K of ROM, our 64K of RAM, and the ability to page ROM and RAM in or out. So let's discuss how we can page ROM out, replacing it with RAM. We need to have a way to indicate if ROM is enabled or disabled, so we just need 1 bit, allowing for a 0 or a 1. Now, if it's a 0, then ROM is enabled and RAM is disabled. If it's a 1, then ROM is disabled and RAM is enabled. So one way to represent this bit is a circuit that can be switched between on and off, and then hold that selection until we change it again. And now there happens to be a component that does just this. It's known as a D-type flip-flop. The 74HCT74 is a D-type flip-flop that can be used just for this scenario. See here in section 2, convert a momentary switch to a toggle switch. That's exactly what we're doing. The lower high that we send to the I/O port is used to set our value, and then the flip-flop holds that value until we change it again. If we take a look at the truth table, you can see that on the rising clock, when D is high, Q will also be high, and when D is low on the rising clock, then Q is low. We can now use this as our signal for paging. And so, if we draw this out, we have the D input, which is the data. And then we have the clock input. Now when the clock input goes from low to high, whatever is on D is copied to the output Q. And the opposite of that is copied to Q complement, which is always opposite of Q. So when the clock rises, the The D is copied to Q and held there. So now let's put this on the breadboard and see how that works. We'll put in the HCT74 and connect ground and power. There. Now let's take a look at the pin out. Pin 1 is clear, which is active low. This will clear the output, setting it to low as well. We'll connect this to the reset line, which will enable the ROM whenever there's a power up or a reset. Pin 2 is D, which is the data input. This is the value that will be stored in the output Q when the clock goes high. Pin 3 is the clock input. Pin 4 is preset, which is the opposite of clear. When this goes low, it sets the output to high. And pin 5 is the output, Q. The other side of the chip is another flip-flop, and we won't be using that. So let's get back to the breadboard and get this thing wired up. Since we're going to not be using the preset, let's go ahead and tie pin 4 high. And then I want to be able to control the value of pin 1, the clear. So I'm going to put this wire in there, and it'll simulate the reset button being pushed. And when that happens, then the reset line will go low. Pin 1 will then set the Q to low, which will reactivate the ROM. So for now, we'll just set that to high. Pin 2 is going to be the data input. And we'll just set that to low for now. Pin 3, the clock, we'll set to low as well, and then we'll bounce that back and forth as we demo it. Now for the demonstration, I'm going to add an LED and a 220 ohm current limiting resistor. And there. So now that we have this set up, what it's going to do is when the clock goes from low to high, whatever is on pin 2 is going to be shown on the LED. So let's demonstrate this and get it plugged in here. Notice how the LED starts out on. This is why we have to tie pin 1 to the reset line. If you remember from the video on the CPU clock and reset, when we turn the power on, the reset circuit is going to hold the reset line low for a second or two. This will then set the Q here to low, indicating the ROM is active. So notice here that when the clock goes from low to high, the LED doesn't change. That's because we have pin 2 tied to ground. But if I put pin 2 on high and then set the clock high, the LED comes on. Set pin 2 back to low and the LED will stay until the clock goes high again. And so we can use this now to indicate that the ROM is active. So how would we activate this? Well, let's take a look at how the Z80 input-output ports work. If we look at the out command, it's made up of the out opcode, the 8-bit port address that we want to send the command to, and the 8-bit value that we want to send. This puts the address, in this case 255, on the lower 8 bits of the address bus. On A0 through A7. And it puts the data value, in this case a 1, on the data bus, D0 through D7. So the address would then look like this on the address bus, on A7 through A0, and the data would look like this, 0, 0, 0, 0, 0, 0, 0, 1. So if we had a way to figure out when the lower 8 address bits were all high, we could use that signal to flip pin 3 high, connect the data to pin 2 to indicate if ROM should be active or not. And to indicate that the 8 lower address lines are all high, we can use an 8-bit comparator, the 74HCT688. And if we look at the data sheet, you can see that it compares A0 to B0, A1 to B1, and so on. And if the enable pin is low, and all of the A pins match the value on the B pins, then the output Y goes low. So, to match the address of 255, we could hardwire all of the B inputs to high and connect address 0 through 7 to the A inputs. And then for the enable pin, we can use the IORQ and M1 signals from the Z80 that indicate it is an IO call, where IORQ has to be low and M1 has to be high. And then if we inverted the Y output of the HCT 688 and connect it to the clock on the HCT 74, when all 8 address lines go high, then pin 3 would go high, sample the D0 input on pin 2, giving us a way to page ROM in and out. What we've discussed up until now is how to page ROM and RAM. We still have to figure out how to enable the ROM and RAM chips and read and write data. So let's switch topics and talk about the chips I'm using for the ROM and RAM. For the ROM, I'm using the Atmel AT28C64 EEPROM, which has 8K of ROM memory. If we look at the pinout, you can see that A0 through A12 are used for addressing the ROM. The CE, or chip enable, enables the chip when it goes low. The OE, or output enable, allows the data to be read from the chip when it goes low. And we can ignore the WE, or write enable, since at this time we will not be writing to the ROM. IO0 through IO7 are the 8 bits that will hold the data when we read from the chip. So in order to read from the ROM, we need a low signal on the read, a low signal on the chip enable, and 13 bits of address. And for the RAM, I'm using an AS6C 1008 128K RAM chip. This gives us room to grow if we choose to page RAM above 64K. And the pinout of the RAM looks very similar to the ROM, except there are more address lines since this RAM is 64K while the ROM's only 8K. We will need a variety of logic chips to interpret the signals coming from the Z80 that'll turn on the RAM or ROM as needed for read or write. If you go back to the CPU architecture video that I did, you'll recall that a memory request is indicated by the MRQ signal going low and the M1 signal high. And then the read and write are indicated by the RD or the WR going low. So we'll need to decode these signals and send them to the chip enable of either ROM or RAM and then the read and write pins. So let's take a look at this truth table I put together. These are the scenarios that we have to plan for. So if we look through these, you'll notice there's only one line that has ROM active. And that's when we're reading from the address below 2000 with ROM paged in. All the other scenarios are addressing RAM. Here we have the address above 1FFF, so RAM's going to be active. On this line, ROM is paged out, so again, RAM would be active. And on this one, it's a write. Now, we need to have a way to copy ROM to RAM if we want to page out ROM, so we'll use the same trick that I used on my Commodore 64. Anytime we write, we want to write to RAM, even if ROM is paged in. A write to ROM area will actually write to the underlying RAM. So let's get into that circuit that I've put together. I have several logic areas I want to review in schematic form before we get to the breadboard. So this is the ROM page select circuit. On the left is the 74HCT688 comparator, and on the right is the D-type flip-flop, the 74HCT74. Notice on pin 1 of the comparator, the input is IOREQ. This signal comes from the next circuit. This 74HCT00 NAND gate takes in the IORQ and the M1 signals from the CPU and outputs the signal needed for the enable pin on the 74HCT688 chip for the ROM page select circuit. IORQ is inverted on pins 11 through 13 and then NANDed with the M1 signal. If you remember from the previous video, IORQ has to be low while M1 is high to signal an IO request. So if we invert the IORQ signal and low becomes high and it's NANDed with the high M1 signal, producing a low, which enables the comparator. This is the comparator for the ROM or RAM select signal. Again, we could have used multiple logic chips, but this reduces the chip count and complexity. The ROM page signal on pin 5, is coming from the D-type flip-flop that we just talked about. To get the RAM select signal, we'll just need to invert the ROM select from pin 19 on the comparator. This is the inverter to invert the ROM select signal to get the RAM select signal, and to invert the output of the ROM page comparator before sending it to the flip-flop. And finally, we will OR the ROM select and the memrec signals to get the ROM enable signal that'll go to the chip enable pin on the ROM, and then do the same thing for RAM enable. I like separating out the logic like this to keep it easy to understand. Now, I know this video started out with a lot of background and logic, but for the memory circuit, it is really needed, and I want to make sure I include everyone in this project, whether you're a beginner or a seasoned vet. So with that being said, let's get to the breadboard. Okay, so here we have the CPU clock reset module that we built in the last video. Now what I want to do first is start out by moving the CPU down a bit to make room for the ROM page select. So let me get that moved over. So there, now we have enough room to add the ROM page circuitry over here. So let's get started on that. Okay, so let's put the HCT 688 right here next to the Z80. And hook up the power and ground. And what we want to do now is hook up the B pins to 5 volts so we have a positive test value, and then hook the lower 8 address pins to the A pins of the comparator. This will compare the address to all highs, or FF, which is the I/O address we want to use for the ROM page select port. So let's get that set up. Now we can hook up the address lines to from the CPU to the comparator. So this output is going to feed the clock input of the flip-flop. So let's get this set up. We'll add the HCT 74 and hook up power and ground. And again, we want to tie pin 4 high since we're not using the preset. Now, we want to invert the output signal coming from the comparator. So let's add a 74 HCT04 inverter and add power and ground. We'll connect the output of the comparator to the input of the inverter, and then we'll connect the inverted signal to the clock input of the HCT 74 flip-flop. So now we have to connect pin 1 to the reset signal, and we'll take that from up here and connect it down to pin 1. And then we'll hook up D0, which is pin 14 on the CPU, and we'll hook it to pin 2, the D input. No, I said pin 14. There we go. That's better. So when all of the lower 8 address lines are high, along with the IORQ low and the M1 high, the low output of the comparator will then be inverted and cause the flip-flop to store the value that's on D0. Since we only have one pin to handle the IORQ and the M1 signals, we'll need to add some logic to get that signal to be low when IORQ is low and M1 is high. So let's go ahead and do that now. If we look at the truth table for the NAND chip, if both inputs are high, then the output is low, and if any of the inputs are low, the output is high. So if we connect the IORQ signal to both inputs, it will effectively invert it. And then we can NAND it with the M1 signal, giving us the low signal to indicate an IO request has been made. So let's expand our breadboard, add power and ground, and then add the 74HCT00 NAND chip. We need to bring the IORQ signal from pin 20 down to pin 13 on the NAND gate. So let's get that connected. And we also need to bring the memRequest signal from pin 19 down to pin 1 of the NAND gate. So let's get that there. Now we need to connect pins 1 and 2, and then the output pin 3 to the input pin 4. And then we'll do the same thing for pins 13 and 12 and 11 and 10. And then we need to run the M1 signal from pin 27 on the CPU down to pins 9 and 5. But let's not run 2 wires from the CPU and bring it down here. Let's bring it down here, and we can use that as a breakout point, like this. There we go. It'll just make for a neater board in the long run. And then we'll run this over to pin 9 and then break it out to pin 5 as well. So the output for the IORQ has to feed the comparator in pin 1. So we'll connect that. So now when we get a low signal on the IORQ and a high M1, the low signal will enable the comparator. The next circuit I want to work on is the ROM select. This will take the write signal from the CPU, the ROM page signal from the ROM page select circuit that we built, and the 3 high address lines, A13, 14, and 15, and compare them to the expected signals to indicate a ROM read. If we go back to the truth table, you can see that write has to be high, and ROM page, A13, A14, and A15 all have to be low in order to enable a ROM read. So if we use a comparator to test these values, we can use the low output to indicate a ROM read, and then invert that signal to indicate we're reading from RAM. This is another reason that I separated the logic for the memory request and the ROM select. If we had included memrec and M1 in this comparator, we would have had to add another comparator to generate the RAM enable signal. And don't get me wrong, there is no one right way to do this. We could have used basic logic chips and got the same results. In my mind, this was simpler to implement and then explain in this video. Before we put this on the breadboard, I want to thank everyone for the views and the comments. I also want to welcome anyone that is new to my channel. Please like the video and subscribe to my channel. It really does make a big difference. I made this channel to share my knowledge and have no sponsorship deals or anything like that, so your likes are all that motivate me. Also, all of the schematics, helpful links for the supplies and equipment that I use, and links to my other channels and my Patreon are available on my website. I have that link below in the description. Alright, let's add the comparator and the power and ground. And also we'll get the test values set up for this chip. If we take a look at the schematic, we want to tie pin 2 high because we want to compare it to a high write signal. Remember that a high write signal means that we're performing a read. Then pins 1, 4, 6, 8, and 11 should all be tied to ground to test against ROM page A13, 14, and 15. And we'll also tie the unused pins to 5 volts so they pass the test. Let's go ahead and get that done now. There, now we have all of our unused pins tied high and the rest of them tied low except for pin 2. Now, let's add our signal connections. We want to connect the ROM page out of our flip-flop to pin 9. So let's get that set up. And then our write signal from pin 22 on the Z80 to pin 3. And then we need to connect A15, pin 5 on the Z80 to pin 12. And pin 4, or A14, down to pin 10. And then A13, which is pin 3, to pin 8. Oh, wait a minute, that's not right. Let's, yeah, that's supposed to be to pin 10. And this goes to pin 8. There we go. Okay, now that we have that connected, we have one last circuit before putting on the memory chips. This is the ROM and RAM enable. This circuit ORs the ROM select and the memrec to signal the chip enable on the ROM chip, and does the same for the RAM signals. The chip enable signal will be active low when both inputs are low. So let's get that on the breadboard now. This is the 74 HCT32 OR chip. We'll get that in here and add power and grounds. Then we want to connect the ROM select, which is the output from the comparator, to pin 1 of the OR chip. And then memrec from the NAND chip to pin 2. So here we have the ROM enable that will go to the chip enable pin on the ROM, right there on pin 3. And now we can do the same for the RAM enable down here. So we first have to invert the ROM select to get the RAM select signal. We could run a wire up here to the inverter we have on the board, but I'm going to cheat a bit and add another inverter chip for the breadboard version. Once we move it to the PCB, we'll reduce it back to one chip. So let's get that and power and ground set up. And then we'll run the ROM select signal from here over to the inverter. And then from pin 2 of the inverter back to pin 4 of the OR chip. Now I also have to connect the memrec signal, which is over here connected to the OR chip. So I will just pull that from the OR chip as well. So now we have the ROM enable and the RAM enable that'll be connected to the memory chips. Our next step is to add the memory chips and begin the fun task of wiring up all the address and data bus connections. So let's go ahead and get that started. Again, we'll expand the breadboard and get the memory chips wired up. On the left is the 128K RAM, and then we've got the ROM on the right there. So let's get power and ground hooked up. Now, when connecting the memory chips, we will have 8 data lines and 16 address lines for the RAM, and 8 data lines and 13 address lines for the ROM. That'll get quite messy if I try to wire things up like we normally do. Plus, the breadboard is going to be taken apart as soon as we convert this to a PCB, which is coming up in a few videos. So, here I have a board that I made for testing the CPU last year. It has several sets of pins for both the data and the address buses. You can see on the back of the card that they are all connected. So I'm going to use this rather than try to custom wire all of these connections. So let's get this connected and see if it works the way I want it to. The first thing I'm going to have to do, though, is replace the address wires going from the CPU to the comparator for the ROM page command. So I'll take those out and replace them with one of these ribbon cables connected to the lower 8 bits of the address bus. The next task is to wire up the non-data and address pins on the memory chips. This will include the read, write, ROM enable, RAM enable. So let's start with the read signal from pin 21 on the CPU. We'll connect it to pin 24 on the RAM. Let's see, 24. 18, 19, 20, 21, 22, 23, 24. Yeah, it's in the right place. Then we're going to connect the write signal. And we pulled the write signal from pin 22 on the CPU earlier. So we're just going to go ahead and connect it here and run it to pin 29 on the RAM chip. And then we'll connect the RAM enable, which comes from pin 9 on the OR gate. And we'll connect it to pin 22 on the RAM chip. There. And so now we have write, read, and RAM enable. Now for the ROM. We'll start with the ROM enable, which is pin 3 on the OR gate up here. And that'll run to pin 20 on the ROM. Oh, come on, pin 3. There we go. There we go. And then we need to connect the read signal, and we'll just pull it from the read pin on the RAM chip. And that goes to pin 22 on the ROM. Yeah, right there. And we don't need the write signal on the ROM, so we'll just ignore that. So now we're going to hook up our address pins for the RAM chip. Because of how these pins are laid out, I'm going to start with A15 and work my way backwards. So A15 goes to pin 31. A14 goes to pin 3. A13 goes to pin 28. A12 goes to pin 4. They're kind of all over the place here. A11 goes over here next to the read pin on pin 25. A10 is on the other side of the read pin on pin 23. A9 goes next to A11 on pin 26. And A8 goes right next to that on pin 27. And the rest of the address is easy because they are all in order from pin 12 to pin 5. So I'll get those hooked up. And now we can do the same for the ROM. Okay, and now we can hook up the data. And these are a bit easier because we have D0 through D2 on one side of the chip and D3 through D7 on the other side of the chip in that order. So let's get this wired up. And then we'll do the same for the RAM. Okay, and now that we've got the memory set up here, let's go ahead and pop this ROM chip out and write a quick program to test it. In order to test the memory, let's copy from ROM to RAM and then page out the ROM. The Z80 command to copy the memory is LDIR. LDIR copies the contents of the memory address in HL to the memory address in DE. It then increments both HL and DE. It also decrements the value in BC until BC contains 0. So if we loaded address 100 into HL and address 200 into DE and 10 into BC, LDIR would copy 10 bytes starting at the address 100 to the address 200. This is a really fast way to copy memory in the Z80. If you tried to use discrete commands, it would take almost twice as long. Let's switch over to Visual Studio Code to get this implemented. Now what we want to do is to copy the program we have in ROM to RAM and then turn off the ROM. The program should keep running, and this will ensure that all parts of our memory circuit work. Since I've designed the circuit to always write to RAM, reading in a value while ROM is paged in will read from ROM, but writing to that same address will write to RAM. So let's start by loading address 0 into HL. And we'll load the same address into DE. Let's plan on copying 255 bytes. We can adjust that later when we know the exact size of the program. Then we call LDIR. After we copy the ROM to RAM, we want to test the RAM paging circuit to make sure it works as intended. So since the ROM is active by default, let's send a command to port 255 to turn the ROM off. So we'll load A with a 1 and output it to port FF 255. Now, conversely, we also want to test to make sure we can turn the ROM back on. So let's load A with a 0 and output that as well. Then let's turn ROM off again so we can test writing to and reading from RAM. A neat way to test that without a display is to have the program write a halt command during runtime, and then we can hook an LED to the halt pin of the CPU and watch for it to go low. So I'm going to add a bunch of no-ops here and then save and compile. This will give me the address of each command so I can then overwrite one of the no-ops with a halt. I'm using Pasmo to compile the assembler. I've got a link for that in my description. I created a simple batch file so I don't have to type the entire command string each time. So let me run that and we'll take a look at the output. Okay, so looking at the output, on the right hand side you can see the commands that I typed in, and on the left hand side you see the memory address followed by a colon and then the command bytes. If we take a look at the documentation for the load HL command, you can see that the value for HL is 10, and that gets inserted into bits 4 and 5. So if we load this binary number into the calculator, you can see that the hex value is 21, which is shown on the output followed by 4 zeros. That's what gets written to the ROM and is executed on the Z80. Notice that the no-ops continue through to address 1C. We're currently set to copy 255 bytes from ROM to RAM, but we really only need to copy starting from the location after the ROM disable command, address 0F, through to the end of the program, 1C. So let's jump back over to our code and change the starting address to 0F, both on HL and on DE. We'll leave the BC register at FF until we add the rest of our commands. Now during runtime, we want to replace one of these no-ops with a halt command. So let's make it easy on ourselves and create a label here called target. What the label does is tell the compiler that anytime you see this referenced in code, replace it with the address that it becomes upon compiling. Let's take a look at the Z80 user guide again to see what the value of the halt command is. So if we write a hex 76 to the memory location labeled target, we will replace that no-op with a halt. So let's go back here and load 76 into the accumulator and then load target with that value. And then recompile it. And there we are. So we're going to start copying ROM to RAM at 0F, and we'll need to copy 19 bytes to the end of the program. So let's make that change in code and save and then recompile. And now let's program our ROM. Okay, we're ready for testing. So let's put the ROM chip back in and test our circuit. We should be able to test this by setting up a few LEDs through a resistor array that I have here with the ground right here, and the rest are just 1K resistors. So let's set this here and get a few LEDs for testing. I think I'm going to do 4 LEDs, and I'm gonna look at ROM page so we can test that circuit. And then I want to see the halt instruction, of course. So I'll hook it up to the halt pin on the CPU. And then we'll also take a look at RAM enable and ROM enable to make sure we're choosing the right chips. Okay, so let's get some jumpers here. And hook one of these up to the ROM page up here on the circuit that we did. There we go. And then hook the other one up to pin 18 of the CPU, which is the halt indicator. And we'll make it the next one over. And then we'll do RAM enable on the next LED over and plug it in right here. And then lastly, ROM enable and get that hooked up. Okay, so if we plug this in, we should be able to see some activity on the LEDs. So we should see the ROM as it reads instructions. The light, you'll see the light flicker because it's actually going off when ROM's active right here. And then we'll see some on RAM, but not a lot because it's only writing to RAM. It's not reading everything from it. And then the ROM page. So let's plug it in. And there we've got the reset indicator, and we should see some activity here. Oh, and there's ROM and RAM. We've got the same number of hits on ROM as we do on RAM. Since it's reading instructions, ROM would have had to go through a lot more cycles. So there's something going on here. Not quite sure what. Yeah, and this is just repeating. It's not even, it's not changing. So let me unplug this, and I want to take a look at the RAM and ROM enable logic. Maybe that's it in the, in the wires coming over here. So I've got the M1 signal right over here that I'm NANDing with the MREC signal. But wait a minute. Wait, that's, oh, I don't, what, yeah, that's not, yeah. Let's that's what the problem is. That shouldn't be there. We don't, the M1 signal is used to is not used at all with memory requests. So let's take this out of here. We don't, the M1 signal shouldn't even be considered. I don't know what I was thinking. So let's get that out of there. We don't need that. Yep, just move this over so it's not even touching the chip. There we go. And then let's take this connector out. We definitely don't need that. Just get rid of it. And then let's pull the MREC signal. Let's just use a jumper and pull the MREC signal from pin 19 of the CPU and dump it down to pin 2 of the OR chip because we don't even, yeah, that was stupid. I don't know where my head was. Okay. This will probably work a lot better now, so makes a lot more sense. All right, that's, yeah, I don't even know what I was thinking. So let's plug this in and see what we get. All right, reset. Okay, and there's the ROM. Yes, exactly. A lot of ROM and some writes to RAM. There's 1, 2, 3. We're copying 19 bytes, so we'll have to have 19 of those. Whoa, that's not right. We only got 4 bytes of RAM written, and then now it's only RAM. Okay, nope. Now they're okay. So, yeah, that's not even close to right. There's, yeah, it's focused on RAM, and somehow it got, yeah, that's not. We're not gonna. This isn't gonna work. Okay, so. That's not okay. So let's yeah, I don't know where it's reading from and why it's reading exclusively from RAM at this. Well, there goes our halt light. Okay. But that, I wonder if there's something. Let me reset it and try this again. Okay, so let's see what we get. Okay, so it's reading from ROM, it's writing to RAM. Now it looks like it's back in that same 2 and 2. This is definitely not right. Hold on, that's different than it was before. So yeah, this is okay. I wonder if maybe if I reseat the ROM chip and test that, maybe it's just I didn't have it in there right, or there's a piece of dirt or something like that in there. Probably not, but let's just take a look at that. Okay, let's see what we get. Okay, reset, and then nope, it's the exact same thing. Okay, but it changed, so I'm wondering if I've just got a bad ROM chip or something. Let me rewrite this. Okay, so I've got this, I reburnt the ROM just to see if it was something, I don't know, that's strange because it changed, so I'm a little worried about that. So let's see what it does, and wait a second. Aha, that's it. Pin 27 there is the right enable pin, and it's not connected. That explains it. So we were writing random stuff to the ROM chip because that's not hooked up. So yeah, that if a floating pin's never a good thing. I should get a t-shirt with that on it. So let's get a jumper here and get this connected. That's a huge faux pas on my part. Okay, there we go. Now let's plug it in and see what's going on with it. Let's watch these LEDs. All right, so we got the reset going, and now we should get activity. Yep, there's ROM. Good. 1. There's RAM. 2, 3, 4, 5, 6, 7, 8, 9, 10. Remember, we're looking for 19, 12, 13. That's the bytes copying. 14, 15, 16, 17, 18, 19. Oh, there goes the, yep, ROM's on, off now. And we're reading from RAM, and we just halted. And now we're in a never-ending loop. Awesome. So this worked. Cool. Well, thank you very much for joining, and yeah, this has been a heck of a build, just so many components and so many wires, but please like, subscribe, ring the bell, whatever you need to do, and visit my my website. I've got all the schematics there and everything. So yeah, again, thank you very much.